Okay, what if I told you that in the near future, a tiny chip in your brain could give you the ability to see, even if you've been blind since birth? Sounds impossible, right? Well, that's exactly what Elon Musk's Neuralink is promising with their new BlindSight brain implant. But can this technology really deliver on such an extraordinary claim? Today, we're peeling back the layers of this mind-bending innovation, examining the science behind it, and asking the tough questions about its potential to revolutionize the way we understand and treat blindness. Now, before we delve into BlindSight, let's first understand what Neuralink is. Founded by Elon Musk and a team of scientists in 2016, Neuralink is a neurotechnology company that aims to develop brain-computer interfaces, or BCIs. Their goal is to create a direct connection between the human brain and computers, potentially revolutionizing how we interact with technology and even treat neurological conditions. Neuralink has been working on various projects, with their first human trials focusing on helping individuals with paralysis be able to control computers and mobile devices using their thoughts. The company has made significant progress in this area, as demonstrated by their first 2 human patients. In March of 2024, Elon Musk used his social media platform X to announce Neuralink's next product after their telepathy brain implant. He called it BlindSight and made some ambitious claims about its potential. BlindSight is the next product after telepathy, Musk posted. I should mention that the BlindSight implant is already working in monkeys. Now, resolution will be low at first, like early Nintendo graphics, but ultimately may exceed normal human vision. This announcement immediately caught the attention of the scientific community, media, and the public. The idea of restoring sight to those who have lost it, or even providing sight to those born blind, is undoubtedly exciting. However, it is important to approach these claims with a critical and informed perspective. According to Neuralink, BlindSight aims to help people who have no eyesight or who have lost their eyes to be able to see by targeting how the brain processes optical information. The proposed technology involves implanting millions of tiny electrodes in the visual cortex, the area of the rear of the brain largely responsible for processing and interpreting visual information from the eyes. The concept behind BlindSight is to bypass damaged eyes or optic nerves and directly stimulate the visual cortex to create visual perceptions. Now, in theory, this could potentially work for individuals who are born blind, or those who lost their sight later in life, as long as their visual cortex is intact. To understand the potential of BlindSight, it's helpful to look at Neuralink's current achievements. The company has successfully implanted its telepathy device in 2 human patients. The first human recipient of a Neuralink brain chip, Arba, is a quadriplegic who demonstrated the ability to control a computer mouse using his thoughts during a live stream event. He was able to play chess and even the video game Civilization 6 on his laptop using the implant. The second patient, known only as Alex, also has a spinal cord injury that resulted in loss of limb control. Before the Neuralink implant, Alex used a specialized mouth-operated controller called QuadStick to play video games. With the implant, he can now control a computer cursor with his mind, allowing him to play fast-paced games like Counter-Strike 2 with improved control and speed. These achievements are significant and show the potential of brain-computer interfaces. However, it's important to note that restoring vision is a much more complex challenge than controlling a cursor or playing video games. To understand the challenges facing BlindSight, we need to delve into the science of how our brains process visual information. Vision is an incredibly complex process that involves much more than simply receiving light signals. When we see, light enters our eyes and is converted into electrical signals by our retinas. These signals travel along the optic nerve to the visual cortex in the back of our brain. However, this is just the beginning of the process. The visual cortex is composed of multiple areas, each responsible for processing different aspects of vision, such as color, motion, depth, and form. Moreover, each neuron in the visual cortex has a particular receptive field, which is the location and pattern a visual stimulus must have to make that neuron fire. These receptive fields overlap, creating a complex network of neural activity that represents what we see. Now, while Neuralink's ambitions are certainly admirable, we can't ignore the elephant in the room. There are some pretty significant hurdles that BlindSight needs to overcome. First off, we're talking about the brain here, and if there's one thing we know about the brain, it's that it's incredibly complex. Vision isn't just a simple on-off switch. It involves intricate patterns of neural activity across multiple brain regions. Trying to replicate this complexity with artificial stimulation? Well, that's a bit like trying to conduct an orchestra while blindfolded and wearing oven mitts. Then there's the issue of resolution. Musk compared the initial resolution of BlindSight to early Nintendo graphics. Now, that might not sound too bad if you're feeling nostalgic, but even achieving that level of resolution is a massive technical challenge. Each electrode in the implant can typically only stimulate a small group of neurons, which results in more of a blob-like perception rather than a clear, pixel-perfect image. It'd be like looking at the world through a foggy shower door than a crisp HD screen. We also need to remember that every brain is unique. The organization of the visual cortex can vary significantly from person to person. This means that a one-size-fits-all approach is about as likely to work as a one-size-fits-all hat. Each implant may need to be carefully calibrated for each user, which is no small task. Long-term stability is another concern. Our brains are pretty good at recognizing foreign objects, and they're not always the most welcoming hosts. The brain's immune response can cause scar tissue to form around the electrodes over time, potentially reducing their effectiveness. It would be like trying to listen to a radio station that keeps getting fuzzier and fuzzier. And lastly, we can't ignore the ethical considerations. I mean, we're talking about putting a computer interface directly into someone's brain. That raises a whole host of questions about informed consent, potential side effects, and the long-term implications of essentially becoming part human, part computer. It's not exactly the kind of decision you make on a whim, like choosing what to have for lunch. So while the potential of BlindSight is exciting, it's clear that there's still a long road ahead. But hey, that's the nature of groundbreaking science, right? It's all about tackling these big challenges head-on and pushing the boundaries of what we thought was possible. To get a clearer picture of BlindSight's potential and limitations, let's look at what experts in the field are saying. Researchers at the University of Washington have conducted studies using computational modeling to simulate what kind of vision a high-resolution cortical implant might provide. Their findings suggest that even with a large number of electrodes, 45,000 in their simulation, the resulting vision would still be quite blurry and lacking in detail. The reason for this, according to the researchers, is that neurons in the visual cortex don't function like pixels on a screen. Each neuron has a complex receptive field, and stimulating a single neuron produces a blob-like perception rather than a precise point of light. Professor Ione Fine, the lead author of the study, explains, even to get to typical human vision, you would not only have to align an electrode to each cell in the visual cortex, but you'd also have to stimulate it with the appropriate code. That is incredibly complicated because each individual cell has its own code. What this research suggests is that achieving high-resolution vision through cortical implants may be much more challenging than Musk's optimistic predictions suggest. As we follow the development of BlindSight, it's important to maintain a balanced perspective. We should be excited about the potential breakthroughs that could improve millions of lives, but also be realistic about the significant hurdles that must be overcome. Regardless of whether BlindSight achieves its lofty goals, the research and development process is likely to advance our understanding of the brain and push the boundaries of what's possible with brain-computer interfaces. This, in and of itself, is a valuable contribution to science and medicine. We want to hear what you think about this groundbreaking technology. Are you optimistic about BlindSight's potential, or do you have your concerns about the challenges that we discussed? Drop your thoughts in the comments down below. If you enjoyed this exploration of cutting-edge neurotechnology, why not join our community of curious minds? Hit that subscribe button to stay up to date with the latest breakthroughs in science and tech. And don't forget to tap that bell icon. That way you'll be the first to know when we release new videos diving into the next big innovation.